So now we want to talk a little more about the physics of what's going on inside a metal. This energy level here that marks the boundary between the filled and the unfilled levels is called the Fermi energy. It's the level that's got a 50% probability of being filled. Now, trying to explain each of these energy levels in full detail is both impossibly difficult and really not very useful to us. Because these energy levels are so close together, we really just want to know how densely packed together they are. And for our purposes, we don't really even need to worry about these gaps or anything. We just need, on average, how close together are the energy levels. So we're going to take a very simplified model of electrons in a metal. We're going to treat them as if they're confined to a box, but within that box they can just move anywhere they like. So under that restriction, we can find, and finding it is above the level of this class, but we can find a probability or a density of states that are allowed to electrons if they were in such a box, that box being the metal. The units are number of states per cubic meter per electron volt. And here we have the energy. So this is the density of states within a certain energy range. And here we show the energy in electron volts. Notice it goes up like a sideways parabola. It turns out this is the formula, and that number density goes like the energy to the 1/2 power. This e to the 1/2 is actually really important for some interesting things that happen, such as Bose-Einstein condensates and superconductivity. And it only happens in 3 dimensions. In 1 or 2 dimensions, it's not there. In 2 dimensions, it's a constant density of states. In 1 dimension, it's actually an e to the negative 1/2. States become less and less common at higher energies. So this is how many states are available to us. But in addition to knowing how many states are available, we need to know the probability that a state would be occupied. Now, we know from our study of thermodynamics that we had the Boltzmann distribution, which had a probability that was proportional to e to the negative energy over kT. And that worked great, but if this energy is small compared to kT, these probabilities get too big. They don't take into account the possibility of having more than one electron in the state. And we need something that will actually restrict that possibility and make it impossible. So instead of using the Boltzmann distribution, we use this probability function known as Fermi-Dirac statistics, or the Fermi-Dirac probability. And it just takes into account the fact that we cannot have more than one electron. If this energy E compared to E Fermi is much bigger than E Fermi, then this is just exactly the Boltzmann distribution, because we can ignore this +1. But if we're at energies much smaller than the Fermi energy, this term becomes essentially 0, and the probability just becomes 1. In other words, at 0 temperature, where it's simplest, this probability is 1 all the way up to the Fermi temperature, and 0 thereafter. At a very high temperature, some of these electrons here can jump from this part very near the Fermi level into this part just above the Fermi level. I want to point out not many of the electrons can. The Fermi level typically has an energy up here in the neighborhood of 7 eV, and even at 1,000 kelvins, the typical thermal energies, kT, are only about 1/10 of an eV. So only the very closest electrons in energy level will jump from their ground states into excited states. which is why I could talk about the conduction happening only at the top of the very top band, and only with those electrons near the top energy jumping up into the conduction region and conducting. Now remember, the reason these electrons have to fill up to these high energies is that you can't fit more than one electron into an energy level, into a particular state. And as a result, we have to go to higher and higher energy states. So even at zero temperature, the highest energy electrons in the metal are actually moving quite fast with a very significant energy of about 7 eV in this case.